Yeah, welcome. So in the last lecture we have been going around with how to update down different networks, and there are three different kinds of updates which you can do is what I was speaking around. So today I am going to actually demonstrate out on how these three different kinds of update rule in a neural network would work. So one of them is where you have all the gradients accumulated at the end of the network, and then within each epoch. So you keep on sending all the samples through it, all the samples whichever you have in your training data, and then you sum up all the errors over there, and then you take a gradient of the error and you backpropagate throughout the network. That is the way of how I was explaining you the whole concept of backpropagation in its own way. There can be another way where say you are not able to handle that much of data. So say that your training data is something like 100 GB in size, your system RAM is limited to some 8 GB or 4 GB. You will never be able to actually put down the whole thing, and your model say it consumes about a few hundred MBs over there, your system OS and everything is consuming, and out of your 8 GBs you are just left with a viable of 5 GB. That is the maximum what you can do. Now, if you load down your data, the maximum data you can load is 5 GB, never 100 GB at a point of time, and in that case we came up with something which is called as a batch learning rule, in which the idea was that you divide this whole set of your training examples into smaller subsets. Each of them is called as a batch. You feed within each epoch, you are going to feed down all the batches. However, you feed one batch, you get your error. Now you can backpropagate that one through the network. Then you feed the next batch, you get your error backpropagated through the network. And the reason why we cannot just accumulate out everything and do a backpropagation is because you have an response of the each layer on your output, which is also multiplied down with the gradient of the error coming down. So that was how our gradient descent was derived. Now since you need to preserve each and every instance's output from the network for updating what's inside the network or the weights over there, so you can use only just a finite number of samples, and you cannot just somehow accumulate over the samples over there. So this kind of a thing is what is called as a batch update rule, and the other one is plain and simple vanilla update rules, in which you put down you put a sample, you get its error, you backpropagate it out, then you put the next sample, you get its error, backpropagate it out. And what this would mean is that say you have some 10,000 samples or 60,000 samples as in MNIST in your training. So within each epoch you will have 60,000 times of an update of the network, which is really large from a computational standpoint. So you will have to compute out gradient for every single sample, that will be computed 60,000 times per epoch, and you will do it. On the other side, if you compare it with the first one, where I am just going to update the whole network at the end of every epoch, it is just once that I am going to calculate out the gradient, and it is once that I am going to do this backpropagation and update over there. So this is a plain difference which comes out, and in fact this has a very significant role when you look at the amount of time it is going to incur. So let us get down with each of them. So how we have divided is we actually have three subparts of this lecture number 24, which is kept on the JIT release for us. So 24A is to do with updating parameters once every epoch. So this is a scratchpad written down for your own understanding of how we change down once we do that every epoch. So our customary first part of the ceremony of running down any code is just to get down your libraries which are there on the header. Next you are going to get down your data. Now look over here that though I defined down something called as a data within a batch size of 100, and that is just from the data loader perspective, it does not have anything to do with my trainer perspective inside over there. Okay. Now I check down my GPU, if that is available, that is well and good, and then now I define my network. And this is the plain vanilla network as we were using down in the earlier example for doing for showing you different kind of cost functions and the dynamics. So here also it is the same one. So you have a 28 cross 28 patch of your handwritten digits in MNIST, which amounts to 784 neurons. They are connected down to 400 neurons. These are connected down to 256 neurons, and this part of it, which is your layer 1, is what constitutes the feature discovery part of the layer with two different hidden neural network layers, and that is connected down to the final classification, which maps down 256 neurons onto just simple 10 neurons, and then this completes down my complete network. Now on the forward pass of the network, what I need to do is given any input to layer 1, I am going to get down certain output, and then I feed that through my layer 2 definition over here, which is my classification part of the wing, and I get my output coming down over here, and this defines my plain simple neural net. Now, if I have a GPU available, then let us just convert it onto a GPU array, so that it is compatible while running out on a GPU, and then we start down our simple classified training routine over there. Now, in the classified training routine, I choose to just do with 10 epochs. This is just to keep it plain, short, sweet and simple. You do not have any issues. A learning rate of 0.1, and the criterion over here, because it is a classification problem which we are just trying to do, we are just going to stick down with the cross entropy loss. Now, you can use a negative log likelihood loss, you can use a multi margin loss, anything as you go down, but we are just going to stick down to simple cross entropy or binary cross entropy loss over here. So, now within my iteration of over epochs, so it is going to iterate over a lot of epochs, and for me it is going to be just 10 epochs over which I am going to iterate it out. Now, over here what I am going to do is one is just starting timer to keep a tab of how long it takes to execute each of them, and that is to show you exactly what is the difference and trade off you get down while shifting from one to the other. Okay. Now, here the first part is basically create down your data loader such that it can keep on loading all the data, and then you in case you have your GPU available, then we are just going to convert my inputs and all the labels into a GPU compatible array, and then you do a forward pass over the network. Now, within each epoch, once you have a forward pass of the network, you get certain output coming down over there. You need to find out your loss. Now, once your loss comes down over there, now what you need to actually understand is that it is going to run over all the batches. So, in your batch loader, what you had done is that it is going to fetch down some 100 images or something. So, let us go down. Yeah, so your batch size is 100. So, it means that technically it is going to fetch down 100 images in one burst from your hard drive. And now, what I am going to do is getting back over here, I am actually going to cumulate my errors over all such ones which are fetched out. So, technically on my training data set within MNIST, you have 60,000 samples. I am fetching down 100 at a time. So, that means that I will have 600 such fetch operations within the within one single epoch in order to get all my data set coming down from my hard drive side over there. Now, when I am calculating out the loss, I need to accumulate all of these losses so that I get down the total error at the end of the epoch itself, and that is what I am just doing it over here. Now, the point which goes down is that I need to find out what is the total loss at the end of being able to load down all of these ones. And now, given the fact that this I which I am using over here, this is a variable commodity. So, for me it comes down that this will be iterating from 0 till 599, and that is equal to 600 over there. And it depends on how many number of batch fetches you had over there. So, that is why I just divided down by I plus 1. Now, this plus 1 comes down from the factor that I is a number which starts from a 0 indexing. So, the highest number which it would get down is 599. In order to get down the total size or the total number of numbers between the range of 0 to 599, that is the last value plus 1. So, that is a simple argument why you have an I plus 1 written over there. Now, after that you zero down your gradients, then you have a backward on the total loss, which is taking down nabla of the cost function itself. Now, once you have this derivative of the cost function taken down, what we will be doing down is actually to do an update following down the vanilla gradient descent approach over there, and that is typically what we do. Okay. Now, once we have this whole thing updated over here, my whole purpose is that let us see what's the validation which comes down over there. Now, for validation we are just going to load down it on my testing data set, which is 10,000 examples over there. Now, for each of them I just get my output coming down, provided a input to this network. So, the network which is updated as part of this particular epoch at any given epoch, whatever is the state of the network. Then we get down our predicted values, and then finally we check if the predicted value is equal to the label over there, and then sum it up in order to get down the number of correctly classified samples over the whole batch, and that is what is going to run out my complete system for trying to do an update once every epoch. You can pretty much see how much time it takes. It takes almost like 2 seconds to complete an epoch, which is pretty fast to say. There are 60,000 samples which are going through it, and it is getting updated at every point of time. However, though the accuracy is not that great over there. So, somewhere around the 10th epoch we are standing at just merely 46% of an accuracy. yes, not something to be really excited at a point of time. However, given the fact that we started with a 10% accuracy, which is perfect. I mean, that's a random coin toss, because you have 10 classes. If you are randomly trying to, so it's something like this. You have 10 buckets, and I am throwing a ball to enter into one bucket, and this ball may enter into the right bucket or it may enter into a wrong bucket. So there is one ball which has the number 1 written to it. If there is a 1/10 chance that it will land into my bucket number 1. The next ball will also have a random 1/10 chance that it will land up into my correct bucket. So technically your random guess accuracy will be somewhere around 10%, whereas once you start learning down over there, so the accuracy keeps on growing, and we figure out that it goes to somewhere around 45% on this case. Now the critical part to see is that it takes roughly 2 seconds to train every epoch, and that's pretty fast over there. Also the loss curve which you see is quite smooth. However, given that fact, there is still a challenge which we were facing down, and that challenge is, if I am not able to load all of those 60,000 samples of data together onto my memory, then I will have to actually update it at every single point of time, and that is where this batch learning rule comes down to play. Now batch learning over here, what we will be doing is, you have a batch size which is set down as 100. So it means that every time you are fetching down some 100 images at one single shot from the drive and then using it. Now once the data loader is done, I check out whether my GPU is available, and voila, once that is there, I have my neural network which is synthesized, and it's the same neural network. So I am not technically changing out anything over there on the network, and that does not need any further definition. So I check out, I get my neural network converted onto CUDA, and then I start my classifier. Now here also I am going to train it over 10 epochs. However, the difference which comes down is in terms of my loss over here, because this loss over here is just what is computed per so you have your loss which is computed over here, which is for every epoch. Now if you remember the earlier one, in the earlier case I was basically calculating out these losses and then accumulating out the loss over here somewhere, which is outside the inner loop which runs over the total number of batches which is loading. So this update over here was happening once every epoch itself, whereas over here you would see this update is happening within every batch itself. So this is present within the inner loop, not within the outer loop, and that is the difference which comes down with a batch loader. Obviously it's supposed to be a bit more computationally expensive. So let me just run it down, because so we can just utilize the rest of the time to discuss around it. Now once you have this updated down, so there will be multiple number of updates which will happen down in every epoch, and then you find out what is the total loss at the end of that epoch, and that is what you are storing down. On the other side, within every epoch I am also trying to do a validation with the test loader coming down over there, and then we will have our timing and all of the other stuff predicted out over there. Now typically you see that here also it takes almost the same time, about 2 seconds to do it, and it starts with a decently better accuracy than you had in the earlier case. Now this should be coming down as a question to you as to why did it actually start with a higher accuracy as compared to what it was in the earlier case, because in the earlier case you did see that like barely it was able to get down to about 45% of our accuracy, whereas here it just immediately started with having 92.7% of your accuracy. Now remember this one thing, in the earlier case the whole network was actually updated at most 10 times, that is the total number of times though everything was getting updated. Here within every epoch it actually gets updated 600 times. So your weights have changed down 600 times within every single iteration what it has done, and now by the end of 10th epoch there have been 6,000 such updates which have happened. Now if you go back to the earlier case and actually run it over an iteration of 6,000 epochs, you would actually tend to come down to the same accuracy level and the same kind of a curve as you are getting down over there. So in the earlier case, if you were running it down initially for 600 epochs, you would be getting down this accuracy. If you have run it down for say 602, which is 1200 epochs, you would be somewhere around this accuracy point as compared to what you are having over here, and that is a distinct advantage which trying to do a batch update. You are taking almost the same amount of time, but you have a much faster way of coming down to a convergence, because the number of times it is actually updating itself and correcting the mistakes which it was making is much large, though it is not updating itself on the same data, it is getting a newer instance of the data and it is looking down. So it is the same thing as say if you are trying to learn up a subject. So the more the number of books across which you study and you give an exam in between or get yourself assessed, the better you are in learning a subject's task, rather than taking a bigger book, a fatter book, and trying to mug it up across the whole semester. So that does not technically always find out a way, whereas if you have this smaller handout books or notes taken down from multiple people and you try to get into a subject, because you are getting exposed to more and more different variants of how you learned on a particular topic. So it's the same thing which comes down as a batch update learning rule for a neural network as well. Now that would bring me to the next one, which is the instance or every sample update, and this is, let us say, the same as you basically read one section of a topic in a book and try to correct yourself for anything else asked on that particular topic, and let us see what comes down, because this is quite interesting, because here what would happen. So let us just do a walkthrough. So the walkthrough is pretty simple. You start with just loading down your initial forms over there, then you do a data loader, and then over here it's just to print down your number of samples, and there are 60,000 samples. So technically that means that within every epoch, if I am going to do an update per sample, so I am going to do that update 60,000 times over there. Okay. Now I define my network, which is the same network. I get it on my GPU, put it down because I have a GPU available, and then I start my training instance over here. I will really set this one running. It's going to take a bit amount of time. In fact, it's a significant amount of time, as you would see down over there. So this is going to run down over 10 iterations. Okay. You see a distinct difference in the learning rate which I have taken down over there, because this is significantly lower than the learning rate in the earlier cases. Now the reason why this is so is you are going to update down at every single sample as it keeps on coming down. Now your total gradient which comes down is dependent very much on what sample was over there. So every sample is not going to have the same range of error. In the earlier cases, because you were taking down an average over all the samples over there, average of the error, so it was getting down to some sort of a average tendency, a lower bound over there, a much more consistent bound between multiple batches which come down in an epoch. Whereas over here, for every single sample, it's going to be either it can be 0 or it can be very large. So if there is a significant deviation over there, there would be a very large error which comes down, and that's going to impact actually the total weight update which you are getting down in your whole thing. Now in order to keep it on a safer side, we would like to put down a learning rate which is lower, so that at any point of time the dynamic range of the weights don't just get overwhelmed by and guided down by the dynamic range in which my updates are changing. So that is the only reason for keeping this learning rate at a lower point of time, and then I basically start my whole iterator over here. Now in the inner range, what I do is, as in the earlier case, I was actually doing a batch loader, so I was able to load down 100 images per batch, but here I am just going to load down one image at a point of time, or this is equal to setting down a batch size of 1, you can say. Now for each image I am going to find down my output, whatever it is, then get down the loss, which is my out of my criterion. Now once the loss is calculated down, we do a zeroing of all the gradients, and then do a backpropagation over find out a gradient of the loss itself on nabla of the cost function, and then write an update rule over here. And here what I am doing is basically I sum up the average loss taken down over each of them. So technically this means that since I have 60,000 examples present down within one single training set in one epoch, so there will be 60,000 times there would be updates happening over there. Now pitch this against the earlier case. In the earlier case you had 600 times of an update per epoch. Here you are able to have 60,000 times of an update per epoch. The downside though is that every time it is with one single sample, so you are not tending to be on the average case of the errors which are coming down over there, as well as you are going to solve much more number of update equations. So 600 versus 60,000, that is 100 times more is the amount of compute which will happen down per epoch over here, and that is how it is getting solved. So the rest of it is pretty simple, that within each epoch, once the training per sample based is over, and then we write down the test data loader which loads up the test example, and then within every epoch I basically try to look into it. So yeah, this actually consumes a significant amount of time. You can see pretty much it consumes almost over 1 minute 4 second, which is close to a more than a minute over there. However, the starting accuracy is really large. You just start down with an accuracy of 96%. Now that's great, right? Because I just saw down all the examples, and at my 0th epoch, whatever it was, it's 96%. Keep one thing in mind, in the first example where I was doing an update over the whole epoch, so that's where I was randomly guessing before I made any updates over here. Here at the end of my first epoch, it's already has been updated by 60,000 times. At the end of my second epochs, it's basically 1,20,000 times that the whole thing has been updated. At the end of third epoch, it's 1,80,000 times that it's getting updated, and that means that the number of times it's seeing and it's trying to update itself is much larger. So if you take the example from the first case where we had just trained it over 10 epochs and there were updates just for 10 times over there, you train it down for 60,000, you would inherently get down an accuracy which matches down about 96% quite easily without much of it. So this is a place where you will have to actually now start to think of syncing and tuning around to play with it as to how they mix and match and work. On one side, while just trying to do one update per epoch is not a great idea, because you will have to run more number of epochs. The other one is trying to do a batch update, which takes almost the same time as doing the update one update per epoch, whereas in the batch update case you actually reach down a much higher accuracy much faster. The other one, which is instance based update or per sample, this is where you would possibly be reaching down the highest accuracy at the shortest possible epoch number. The time consumed per epoch is going to be significantly large, and that's really problematic. If you can think of sparing that amount of time, it's well and good, but for most of us that's not a practical feasible solution. And for that perspective, we do understand that actually trying to have a batch update rule is a much practical approach to do it, and which is what is followed down. In fact, the way that data loader was written, the reason why we were loading out in batches and trying to do is everything is guided, because this learning rule itself is much more better and comprehensive. So it's a good trade off between trying to reach down your saturation accuracy to the amount of time you take to reach down that accuracy per epoch. So if you look into it, that what is the total number of seconds I have spent in order to come down to say 96% of an accuracy. So over here, this is going to be somewhat like 1 minute 4 second is when I come down to a 96% of an accuracy, as compared to this batch update where I was able to come down to 96.7% of an accuracy within just the fourth epoch, and that's like 2 seconds per epoch. So it's basically 8 seconds is my total time taken down in order to come down to the same accuracy, as versus 1 minute of time to come down to an accuracy which is closer to that in this first case. And that's a significant advantage of trying to use a batch update, and why we would be sticking down to that. Now, since I have kept it running for 10 epochs, you just have to wait over it. Whereas if you look into this accuracy facts over there, you see that after some point of time it just doesn't increase to that much of a level. So the amount of time I am spending down in going down from 96% of an accuracy to say 97% of an accuracy is close to about more than is about 7 minutes. Let's say 1 minute 4 second into 6 is close to about 7 minutes, whereas it doesn't actually pay off. In 7 minutes you have been able to just gain 1% of accuracy, as compared to the earlier case in a batch update where like just within 2 seconds you have been able to see a change in accuracy of 3%. Now that's a significant change which comes down, and this initial curve that in the first 2 seconds itself you reached out about 92%, and that compared to here where it took you almost a minute to reach up to 96%. So these are simple tricks around the point of why we would be using one and not the other way of doing it down, and what can be a better way of doing. The other point is that within a batch update you definitely save out on a lot of your RAM space. You might not have enough of space to load the whole data set, but again just loading one single sample at a time is also not a feasible. You are going to spend a lot of time just doing a hardware IO operation. You are going to fetch down something from your hard drive and then copy it down. So there is a significant amount of DMA transfer operations which is involved over there, and since typically your DMA buses, so from your knowledge of computer organizations and operating systems, you do understand that your DMA bus is almost like 10 times or even 20 times slower than your CPU clock and the bus between your CPU to your RAM, and that's going to guide it down. Whereas you can do a batch update, say a significant number of throughput updates over there, and with a batch loader, this is where you basically come down to a advantageous position as versus doing it with just one single sample at a point of time. So if you look down, so somewhere around 8th epoch, which is almost close to 9 minutes that we have been speaking around, it is somewhere at 1.7% of a change which is there, and that's not something which is appreciated in any way for your own practical purposes. So let's just wait for some more time, and we can actually see the same kind of a curve coming. However, if there is one crazy thing over here, instead of trying to plot down, what we plot over here is basically the loss at every epoch. Now the whole point over here is that instead of trying to plot the loss at every epoch, let us try to plot the loss after every single sample as it keeps on going. You would see a very crazy curve, like it will come down as a jittery curve, and in certain times you would see that it rises up, then comes down, then rises up and comes down. But however, the average trend over that particular line is something which will follow down. Now compare that with a learning curve for every batch itself, you would see that every batch one has a much smoother decrease as it goes down. So I'm almost done with my 9th epoch, and if we wait for some more time, you can actually see the 10th epoch going out. Now look into one point. This is what we call as a point of inflection. This is where you see that the test accuracy over there has actually started decreasing. Now this is a point in classical learning theory is what we call that the network has started to memorize whatever has been given down to its training example. So it's getting into something which is called as an overfitting problem. It's very good, it's reducing down the error. If you look into these losses, the loss has decreased because this loss was computed on the training data set itself, whereas this accuracy is decreasing instead of increasing. If your loss was decreasing, then your accuracy should be increasing, whereas here you see that your accuracy had decreased over here as compared to this one. It suddenly again increases over here, does increase, but this is a point of inflection which is now starting to happen over here, and that's something called as an overfitting problem. So later on in the other lectures, we will be going down to how to identify these points of inflection and when the overfitting is happening, and what you can do to actually cut down this issues of any overfitting happening. So you can typically see like around these epochs is when it started these inflection, and from our experiences we know that once it is at this point and beyond everything, it's actually trying to memorize the network in a big way. It's trying to pull itself out though of that practice, but this is something which happens if you are training it over a longer period of epochs. So with that, we have done some basic understandings of the different kind of learning rules from your global updates per epoch to batch updates to single sample based updates, and the pros and cons around with that. So stay tuned and till the next lecture comes up. Thanks.